Hello everyone. Today I will share some of my recent thoughts on my research on good electrolytes for carbon dioxide reduction. To do it so, I will start explaining the Wadding graph. So, talking about the work of Professor Angel, who classified the electrolytes in general using this plot, using the behavior, the viscous conductor behavior. Thereafter, I will apply a criterion to this plot to add to identify good electrolytes for electrocatalysis, and I will make MAPIC, which is liquid ammonia, and I will discuss why it would be in a good pick based on the predictions of high content of carbon dioxide absorption, and discuss the mechanism of liquid ammonia dehydrogenation and liquid ammonia carbon dioxide reduction induced by plasma electrochemistry. Professor Angel also had performed several analyses using the Wonder plot, which basically plots in a graph in the x the inverse of viscosity, and on the y's the molar conductivity. On this left side is one of his first publications on this topic, and you see that this vertical line here is the normal behavior for aqueous electrolyte. Anything that falls above is called superionic liquid, falls below is subionic liquid. So he evolves his idea until have this graph at the right side, where he classified the electrolytes in a huge range of either viscosity numbers and ionic conductiveness range of values. To give you an idea, aqueous potassium chloride is located in this point here in this graph. Ionic liquids is located nearby here in this region. Pure ionic liquids right below this region, so it has the same mechanical behavior, but it has a very lower conductiveness. Super ionic cooled liquid is located here in this region. It's more viscous, but could have a greater value of conductiveness in this region. What have I done? Well, I updated this graph. How? Employed searching recently prepared and characterized ionic liquids, which in my opinion could be good candidates for a technological reactor to be employed for electrocatalysis of carbon dioxide, for instance. Here, so we have in this region imidazolium-based ionic liquids. In this region, good ionic liquids, and here a sort of super ionic liquid. And as you see here, there is some colors to the angel classification. And now I should say, give you some examples of electrolytes already used, tested for electrocatalysis. And the first one is the ethylamine, which in this case is a sort of super ionic liquid. In here, in these photographs, you see a rotating electrode before, during, and after the electron reduction, the electrochemical experiments, and you see that several bubbles were trapped in this liquid because it's so viscous that do not allow the produced gases escape the liquid. And this will be the highly viscous electrolyte, despite a very good conductor, is not suitable for electrocatalysis once it prevents the escape of final products, the gases. Another chance was given for a traditional organic electrolyte, acetonitril, and I ask you to keep in mind an information in these experiments that carbon dioxide reduction reaction occurs along with the electrolyte degradation, as is an inherent fact, and this is important when designing industrial reactors, because having a residue introduce an extra cost for the reactor. Now I show you my updated plot where I want to apply two criteria. First one is the minimal conductiveness. In my experience with electrochemistry, potassium chloride 1 millimolar is the minimum value of support electrolyte to give a good ionic conduction for a conventional electrochemical cell. So I use this value here for my first criterion. The second one goes to the maximum viscosity we should admit to an electrolyte. And I pick a value from the petrol oil industry that uses 500 millipascal as a benchmark value for bumping liquids without so extra cost. If one could pumping a liquid inexpensively, it would also be a good reference for us to allow gases to escape the electrolyte. It's just a criterion. You can use another. This is my criterion, so we could flexibilize. We could make it more constrained in this value and assume 100 millipascal. And we have this green area, this highlighted green area, as the area good for electrocatalysis. Now I should comment the liquids, the points in this graph. So only to give you a reference, water and salt is a conventional electrolyte for batteries. It falls over here. Conventional organic chemistry, electrolytes for organic chemistry like acetonitrile dimethylsulfoxone falls in here. Ionic liquids could have a wide behavior, mechanical electrobehavior. It could go from non-conductor up to a super ionic conductor and viscose. It behaves like a gel, or it could fall right in the region perfect for electrocatalysis, like is the case for pyrrolidinium based ionic liquids. And I will call attention to liquid ammonia that falls over here and hydrazine that falls right below. I would suggest that ammonia would be a good candidate for carbon dioxide electrocatalysis because liquid ammonia, despite not tested for absorbing carbon dioxide, we know from the basic knowledge that it would certainly absorb the high content of carbon monoxide, because we know from the work, previous work, that aqueous amine absorbs half molar of carbon dioxide per each molar of methylethanolamine. And the chemistry of this absorption is that carbon dioxide reacts out with liquid ammonia, producing a new organic function called carbamate. That's the basic mechanism of carbon dioxide absorption by nitrogen-based electrolytes. As I said at the beginning, I would put much attention on the plasma electrochemistry. And from this perspective, I could say that dehydrogenation of liquid ammonia would be produced by the cathodic plasma, because it is well known that this polarity introduces solvated electrons in liquid phase. The hydrogen production used by solvated electrons were already discussed for liquid water. Based on this mechanism, I could say or suggest what would be the mechanism for liquid ammonia, because in liquid ammonia we don't have acidicity, so reactions 6, 7, and 8 would be suppressed in liquid ammonia, resting only the possibility for high hydrated solvated electro-soft recombination in ammonia, which would give hydrogen plus the conjugated acid, the basicity of ammonia. What about carbon dioxide reduction mechanism? I would follow the same rationalization using the mechanism already studied for water and related it with what would be expected for liquid ammonia. Again, the carbon dioxide mechanism was already investigated, and I would tell you that given the fact that liquid ammonia does not have acidicity, this reaction 6, 7, 8 will be suppressed, as well as the reaction 3, as the carbon dioxide absorbs in liquid ammonia as carbamates. So reaction 5, 10, and 9 would be also suppressed, giving, allowing for this possibility here. It's completely a speculation, but still I could give have some clues on how the carbon dioxide would reduce in liquid ammonia. My suggestion, sulfate electron would react out with the carbonate, giving resulting in formic acid as the marginal final product. Again, this is a suggestion. This community, the plasma community, to go home and give liquid ammonia a try to check it out, which would be the final product. As a promise in the abstract, I would say I would also comment the mechanism for anode plasma, or the positive polarity of plasma. In this case, we could make some rationalization based on the work of Hickling that observed the formation of hydrogen. This guy here, hydrogen, out of ballistic cation injection in the liquid ammonia. So, as he identified this phenomenology, I would suggest that the mechanism in this case is liquid ammonia produces the radical, the basic ammonia radical, that in a second step recombines from hydrazine. How would be the final product in case liquid ammonia is enriched with carbon dioxide? I would suggest that either the ammonia radical reacts out with the carbonate, or the carbonate itself is split by ballistic cation, and I will not speculate the final product in this case. So, message to go home. Plasma electrochemistry in the plasma community should give liquid ammonia a try. Thank you for your time.